I think. I don't know, maybe I got past it. But there's some things that happen when you take the second derivative. I know that we all at least got to the first derivative of that function, which was, where is it? There's the first derivative. We were good to go there. And then you had to take the second derivative, and I want to talk a little bit about taking that second derivative because it puts a lot of puzzle pieces together that we've talked about earlier that didn't seem to make much sense. Like, for instance, not multiplying out denominators. And in this case, you actually don't want to go crazy simplifying the numerator, and I'll show you what I mean. So, second derivative is there, and hopefully you can all follow me on that. Bring the denominator up to the top, multiply by the derivative of the numerator, minus, I should have some big honking parentheses around that, but the numerator times the derivative of the denominator, and there's some chain rule in there, and everything's good to go. Now, I know on Friday when some of you were doing this, you went crazy and started multiplying out the binomial and doing all kinds of other things. However, if you don't do that, it actually is a little bit easier. So what I would do is the following. I would just click on this like an idiot. Where was I? Okay, there. All right, now, negative 12 times x squared plus 3 squared. Don't change the beginning very much, but if I take the 12x, the 2, and the 2x and multiply that together, I get positive 48x squared times x squared plus 3 all over x squared plus 3 to the fourth. And so like I said on Friday, some of you multiplied out that binomial, then you distributed the 48x squared, and it's calling to you. It wants you to distribute it. Come and distribute me. It'll be fun. It'll be a quartic. Everybody loves working with quartics. Come on, get in the van. I've got candy. You know what I'm saying? But don't be lulled into getting into the van. Just stop here and look at a GCF. So the GCF between these two things is 12x squared plus 3. And you'll recall we talked about taking the smaller exponent. So in this case, I would only take one of those x squareds. What's left behind? Well, I'd leave a negative x squared plus 3. And then I'd have a 4, so plus 4x squared. Okay. Then I would cancel this and make this a 3. That makes my life a little bit easier. And then I would simplify this stuff in the brackets, which would give me a 3x squared minus 3. Which would give me 3x squared minus 3 would be x squared minus 1 times 36 all over x squared plus 3 to the third power. And after all that garbage, it simplifies into that nice little thingamajobber. The question is, where are the critical numbers? Plus or minus 1, and what about the denominator? Did we talk about this on Friday? What makes this denominator equal to 0? Nada. That's Spanish. Critical numbers, plus or minus 1. There is nothing that I can put into the denominator that will allow that to be any real numbers that I can put in the denominator. So now I just have those critical numbers at 1 and negative 1, which is what I get there. Okay? So then, the book likes to do this. The book likes charts. That's icky. I like this method better. Second derivative number line. This becomes very important now. It didn't seem that important when we were doing just a first derivative number line, but now all of a sudden we've got a second derivative number line, and hilarity ensues. That tells me not only what number line I'm looking at, it also tells me where I'm plugging numbers into. So I would plug in like negative 10, 0, and 10 to see that it goes from concave up to concave down to concave up. What happens at 1 and negative 1? Do you recall? It's a point of inflection, correct. When we do the first derivative number line, we were concerned about whether or not it goes plus to minus, because if it goes plus to minus, is it a max or a min? It's a max. And if we go minus to plus, it's a min. This doesn't matter. If it changes either way, or there's just a change, then we have a point of inflection. Okay, anytime the second derivative changes signs, we generate a point of inflection. It's a concavity change, which is exactly what that looks like. And there's the fancy definition, which we don't care about because we already talked about it. It's where the concavity changes concave up to concave down to concave up. Whoosh. Okay. So let's do this one. Find the points of inflection and tell me the concavity of the graph on certain intervals. Go, dog, go. Yeesh. This guy right here. See, you wash
Yeah, I know.
Easy, let All right, so yeah, so 0, 2, yes. Okay. Don't assume that they're both points of inflection. Put them on a second derivative number line and test regions. And I think in this case, walking around, it turns out they are both changes in concavity. Rita, what was it? Concave up, concave down, concave up? Or the other way around?
Yeah.
Concave up?
Yeah.
Concave down, concave up. I think I might have that in here somewhere. Yeah, there we go. In case you're wondering, that's what the picture looks like. It's a quartic. Looks like a weird W. Easy? Yes? Beautiful. Let's move on to something not easy. Oh, that would have been the end of Friday, but we ran out of time. Okay, so before we delve into the second derivative test, I have to give you a disclaimer. If it were up to me, I would not teach the second derivative test because it will confuse many of you. It does exactly what the first derivative test does for us, but it doesn't do it as well. So you're asking yourself, why is he teaching us something that we can already do with something that always works when in fact we're going to do something that doesn't work? Like I said, I would not teach this to you, but with my luck, the very first question on the AP test will be, use the second derivative test to blah, 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 blah. So at least I can say I showed it to you. What it does is exactly what you expect it to do. It finds maxes and mins. It just does it in a different method. It uses the second derivative instead of the first derivative. Okay? So there's my disclaimer. Everybody with me? I'm going to do it anyways, and we'll see what happens. It deals with a pretty straightforward concept, and that is, let's suppose I've got two critical numbers. Critical numbers at x equals plus or minus 2. I have no idea what the graph looks like, but I do know that those are critical numbers. In other words, f prime of x equals 0 at these 2 points. Let's talk about x equals 2 first. So at x equals 2, we know it's a critical number, which means it's either a max or a min, but it's concave down. The graph is concave down. Would it be a max or a min? Why? Right. I mean, and it seems silly, but this is a really good explanation. Right? Everybody with me? I sometimes use this. It's concave down. That's got to be a max. Are we good? Yeah. Okay, good. At x equals -2, it's concave up. And, I mean, you're all fairly bright. Max or min? It's a min. It's concave up with a critical number. It's the bottom of a parabola. Does that make sense? Hot diggity. We're done with the second derivative test. All right, I'm kidding. We're not done. But that's pretty much it. If it's a critical number from the first derivative and it's concave down, it's going to be a maximum. Okay, now another way of saying that it's concave down would be f double prime of x is less than 0. Or if it's concave up, f double prime of x is greater than 0. If it's a hill, then you got a max. If it's a valley, you've got a min. Which is what that says. Now, this is the problem. It doesn't always work. The first derivative test always works. So again, why would we do something that's more complicated and doesn't always work, and I don't have an answer for you? Except that some chucklehead's going to ask you a question about it on the AP test, and I want you to at least have seen it. This will make more sense when you see it in action. So let's take a look at this nice little quintic. You love quintics. Okay. And I'm going to take you through this to show you what it looks like. First of all, I have to find the critical numbers. I have to find the places where we could possibly have a max or a min. F prime of x. Armin, what's the derivative of f here? Well done. Which is the same thing as factor out a negative 15x squared. I would get x squared minus 1. Therefore, my critical numbers would be at x equals 0, positive and negative 1. Now, what most of you will do is use the first derivative test. Put those numbers on a number line, test regions by plugging in the first derivative, find out if they're positive or negative, which would be increasing or decreasing, and you're done. But it's this little catch right here, using the second derivative test. So we have to use the second derivative. But we're going to use it wisely. I'm not going to do more work than I have to. One thing I have to do is find the second derivative. Armin, back to you. You're on a roll here, buddy. What's f double prime of x?
It would be
Keep going. Come on, you got it.
x to the third.
You're good. You're done. Okay. Okay. Now, I could set that equal to 0 and do a bunch of other work, but I don't care. All I care about is that at those three numbers, 0, 1, and 2, whether the second derivative is positive or negative. So to make my life a little bit easier, I am going to factor it. And again, I do know that if the second derivative is equal to 0, then blah, blah, but I don't care. I just care about x equals 0, x equals 1, and x equals negative 1. So let's do 0 for, we'll save 0 for the end. At x equals 1, f prime of 1 equals 0. That establishes that it's a critical number. And f double prime of 1, is it positive or negative? It's negative. Which means concave up or concave down? Concave down. So is x equals 1 a max or a min? Concave down. Max. Beautiful. All right. X equals -1. F prime of -1 is equal to 0. Critical number. F double prime of -1. Greater than or less than 0? Concave up. It's greater than 0. A negative times a negative, which makes it a min. Concave up with a critical number, bottom of the curve. Now the weird one. What happens at x equals 0? Well, f prime of 0 is equal to 0. That's good. We knew that already. It's a critical number. But what about f double prime of 0? It equals 0, which means we're done. We can't use the second derivative for it. We don't know. It could be a max, it could be a min, it could be neither. The second derivative won't tell us that. Wait, yes, sir?
So like on the AP test, if it says use the second or find the second derivative of whatever, and you can't, do you just use the first derivative answer?
If the problem was worded just like this on the AP test, you would say that this is a max and this is a min, and say that it fails at 0 and be done.
Okay.
However, they will also phrase it sometimes saying using the second derivative test or the first derivative test if the second derivative test fails, which is ridiculous, because why not just do the first derivative test and quit screwing around? Hence my frustration and why I wouldn't teach it. But again, they're going to, it's a catch-22. If I don't teach it, it's going to be there. Now that I've taught it, we'll never see it.
Great.
Yeah.
Is this on the quiz?
I'm sorry?
Is this going to be on the quiz?
Oh, yeah.
Okay.
Yeah, I'm still going to quiz you on it. But I don't know about the College Board. They don't ask me what I think. Ever. Oh, look, there's all the work we did. Good, beautiful. Yep. Oh, and guess what? The second derivative test also has its own sentences. But we did those already. Now notice, this is a crucial idea. The second derivative test has absolutely nothing to do with concavity. Yes, we're talking about concave up and concave down. But the second derivative test doesn't test for concavity as far as is it concave up or concave down. It uses concavity to figure out whether you have a max or a min, which even more complicates it and confuses it. I apologize. When given the option, 99.9% of you will do the first derivative test, and I don't blame you, I do also. And unless the problem specifically says to use the second derivative test, then stay with that first derivative test, because it's easy peasy lemon squeezy. But occasionally, somebody's going to want you to put on your big boy pants and do a second derivative test. Or big girl pants, sorry. Big person pants. It's 2019, I should be more sensitive. In case you're wondering, that's what the graph looks like. Relative max at 1, relative min at -1, and nothing exciting at 0, except, well, you tell me what happens at 0. Point of inflection that's going from concave down, concave up. We are done. Beautiful. Discard. Right here.